Here are the learning objectives for this video. Identify and set up a Bernoulli differential equation. Use substitution to convert it into a linear differential equation. Solve the equation using an integrating factor and apply an initial condition. Welcome! Today we are going to solve a classic differential equation problem, often referred to as a Bernoulli trap. We are asked to solve the differential equation dy dx plus y equals y squared times the quantity cosine of x minus sine of x. We are also given the initial condition y of 0 equals 1. At first glance, this looks almost like a standard first-order linear differential equation. However, the y squared term on the right side prevents us from solving it that way. This specific format, where we have a function of x times a power of y on the right side, is known as a Bernoulli differential equation. To solve it, we need to use a special substitution to transform it into a linear equation that we already know how to solve. To transform this Bernoulli equation into a linear one, our first step is to eliminate the y squared term on the right side. We do this by dividing the entire equation by y squared. This gives us y to the negative 2 times dy dx plus y to the negative 1 equals cosine x minus sine x. Now we introduce a new variable, let's call it v. The standard substitution for a Bernoulli equation is to let v equal y to the power of 1 minus m, where n is the power of y on the right side. In our case, n is 2, so we set v equal to y to the negative 1. Next, we need to find the derivative of v with respect to x, so we can substitute it back into our equation. Using the power rule and the chain rule, dv dx equals negative y to the negative 2 times dy dx. If you look closely at our modified differential equation, you'll see that the term y to the negative 2 times dy dx is exactly what we have, just without the negative sign. So, we can rearrange our derivative to say that negative dv dx is equal to y to the negative 2 times dy dx. Now we are ready to substitute v and its derivative back into the equation. Let's carefully substitute our new variable, v, into the equation. We replace the first term with negative dv dx, and the second term, y to the negative 1, simply becomes v. To put this into standard linear form, let's multiply the entire equation by negative 1. This gives us dv dx minus v equals sine of x minus cosine of x. Notice how the terms on the right side flipped signs. We have successfully transformed our Bernoulli equation into a standard first-order linear differential equation. To solve this, we need to find an integrating factor. The integrating factor is e raised to the integral of p of x dx, where p of x is the coefficient of v. Here, our coefficient is simply negative 1. Integrating negative 1 with respect to x gives us negative x, so our integrating factor is e to the negative x. Now we will multiply our entire linear equation by this integrating factor. Let's take our linear equation and multiply every term by our integrating factor, e to the negative x. This gives us e to the negative x times dv dx minus e to the negative x times v equals e to the negative x times the quantity sine x minus cosine x. The magic of the integrating factor is that the left side of our equation now perfectly collapses into the derivative of a product. By reversing the product rule, the left side is simply the derivative with respect to x of v times e to the negative x. To solve for v, we need to integrate both sides with respect to x. The integral of a derivative simply leaves us with the function inside, so the left side becomes v times e to the negative x. For the right side, we have to integrate e to the negative x times sine x minus e to the negative x times cosine x. You could use integration by parts here, but if we look closely, we might spot a shortcut. If we take the derivative of negative e to the negative x times sine x using the product rule, we get exactly the expression inside our integral. Therefore, the integral of the right side evaluates simply to negative e to the negative x times sine x plus our constant of integration c. Now we are incredibly close to finding our general solution. We left off with v times e to the negative x equals negative e to the negative x times sine of x plus c. To isolate v, let's multiply the entire equation by e to the positive x. This cancels out the exponential terms on the left and on the sine term, leaving us with v equals negative sine of x plus c times e to the power of x. Remember, our original equation was in terms of y, not v. Earlier, we defined v as y to the negative 1, or 1 over y. Let's substitute that back in. So 1 over y equals negative sine of x plus c times e to the power of x. Taking the reciprocal of both sides gives us our general solution. Y equals 1 over the quantity c times e to the x minus sine of x. Now, we must apply our initial condition, y of 0 equals 1, to find the specific value of our constant, c. Plugging in 1 for y and 0 for x, we get 1 equals 1 over the quantity c times e to the 0 minus sine of 0. Since e to the 0 is 1 and sine of 0 is 0, this simplifies beautifully to 1 equals 1 over c. Therefore, c must equal 1. Substituting c equals 1 back into our general solution, we arrive at our final answer. The solution to the differential equation is y equals 1 over the quantity e to the x minus sine of x. Let's recap our learning objectives. First, we successfully identified the Bernoulli form and divided by y squared to set it up. Second, we used the substitution v equals y to the negative 1 to transform it into a solvable linear differential equation. Finally, we solved it using an integrating factor and applied our initial condition to find the exact solution. Great work working through this Bernoulli trap.